Welcome back to the show that tells you you are a quantum computer with free will that somehow does not get stuck in an infinite loop. The topic for today will be epistemology. How do we know what we know? To begin our discussion of epistemology, we'll be viewing the limitations of digital computers through the lens of first-order logic. These examples of limitations in first-order logic come from Gödel's incompleteness theorem, Bertrand Russell's set paradox, and Alan Turing's halting problem. By the end of today's video, we'll get to the question, are quantum computers the answer to the never-ending loops and the infinitely arising paradoxes that come out of first-order logic? And most importantly, will you, the viewer, finally appreciate the fundamental problem of taking the human mind and trying to describe it with a digital computer? If you find this interesting, then please like the video, subscribe to the channel, leave a comment below, and write a review.
Join me deep inside the mystery of numbers. Come and huff a metaphysical glue. See how concepts become objects and then become qualia. Join us for an episode of Quantum Consciousness.
Hey there, welcome back. I'm excited to be here today with you. So we're going to talk about epistemology. Epistemology is how do we know what we know? And one of my favorite quotes that really encapsulates this notion of epistemology is from Albert Einstein. And it goes like this: the most incomprehensible thing about reality is that it is at all comprehensible. And what is so amazing about this is if you really think about it, how do we know what we know? We have so much knowledge and so much facts and data that we hold in our head, and we assemble this data into theories that we use to predict the future or just to make sense of our world. But what is that framework of understanding, that framework of knowledge that we're using to draw inferences and make conclusions and to really guide ourselves into our future actions? So today I'll be breaking it down into a few different subcategories of epistemology, or different forms of understanding and creating structures of meaning. So I'll be using the three-world model, which was introduced in a previous episode. But at the most simple scale, we have deduction. And I've put this in the physical world, and you'll see why, and you'll appreciate that more to come. But deduction is based on first-order logical principles. If this, then that, true or false. Everything is binarized into a yes or no sort of reality. And using deduction, we can form simple logical systems and draw conclusions. And this is fundamentally what digital computers are. And I'll really make that case today. In a later episode, we'll be talking about inference and induction. And induction is the system by which we see a pattern and then we draw an inference into future observations. So a lot of this has to do with sort of Bayesian models of how things take in information, update your current working model, and then you project that into future predictions. And this fits nicely with the mental world, and a lot of human logic can be viewed as fundamentally inductive. Finally, we'll be talking about abduction, a lesser-known key term here. And abduction is the creation of theories or general theories of knowledge, systems of understanding. And this really finds its home in the Platonic world, or that domain of meaning and concepts. And this is really abstract thought. And we'll come back to this in a later video at the end of this epistemology series. All right, so let's kick it off by talking about first-order logic. As I mentioned just previously, this has to do with Boolean variables. And Boolean variables are true or false. There's no such thing as truth 0.5 or false 0.5. There's no space between true and false. You have true and you have false. There is no gray area in first-order logic, right? Every single variable, let's say we have X or Y or Z or P or Q, these are going to be true or false in our system of first-order logic. Next up, we have propositional statements or propositional logical statements. And this is something like, if P, then Q. So if P is true, then Q is true. And a very simple first order logical principle is what's called modus ponens. If P, then Q, and we know that P is true, therefore we draw the conclusion that Q must also be true. From that same propositional logical statement, we also have modus tollens. And modus tollens is if P and Q and not Q, then now we know not P. Because if P were true, then Q would have to be true, but it's not. However, fun to think about, if you have P being false, then you actually don't know anything about Q. Q could still be true. And first order logic is really wonderful because of how simple it is. And digital computers are fundamentally based in first order logic. So while this seems like, maybe some fun thought games or like an oversimplification of human logic, in the digital computer framework, we have binary, we have transistors. This transistor, which forms the fundamental bit within a digital computer, can either be 0 or 1, and it can't be 0.5. There is no 0.5 in a digital computer at this foundational level. And so when we run an algorithm or a system or a program through this digital computer, we say, if you see a 0 followed by a 1, output a 1. If you see a 1 and a 0, output a 1. Right? You can have any sort of logic table or these logic gates that instantiate these sort of propositional logical statements. And so essentially a digital computer and any sort of algorithm is fundamentally built up out of first order logic, out of these propositional statements. And so all of digital computation and modern, information technology is fundamentally based in this first order logic. So it may seem like an abstraction at first, but this is actually very core to our modern technology. And so let's say you out there believe in artificial intelligence and you believe that there's some algorithm that could one day recreate the human mind and we could engineer a conscious being in silicon or in a digital computer, then you are essentially asserting that that artificial intelligence or that human mind is a first order logical system. Fundamentally, by definition, you are asserting that it's first order logical. And so what we can do is we can look at history and how did mathematicians understand first order logic, because if we're running around identifying with digital computers, it's important to then look at what are some of the problems that arise in first order logical systems and what can we take away from that and then extrapolate into these models about digital computers relating to human consciousness. So one thing that really blows my mind, and I think it'll blow your mind, is that we don't really understand mathematics fundamentally. We all have an intuitive grasp of mathematical concepts, and this is why it's so confusing. And I'll lay it out for you here. We understand a square, we understand parallel lines. You can go sit in math class and you can learn all this stuff about mathematics. But if you try to get at the foundation of math and you try to say, let's use first order logical principles to derive all of mathematics. And this seems intuitively possible. I think most people, when they first hear about this, go, oh yeah, that has to be possible, that we can take mathematics, reduce it down to true or false statements, and then build up all of mathematics from this logical system. And then after we've built this logical system, it all checks out, it all makes sense. We've therefore derived all of the things that we understand intuitively and that we, when learning these proofs or learning mathematics in school, we now have a system of logic that can, at a fundamental level, sort of make sense of all of that with, among itself, between different principles and all that jazz. And so this is called the foundation crisis, because people tried to do this. It seems intuitively possible. It seems like this would be fundamentally something doable, right? And probably someone out there has already done it. Well, people have attempted to do this. And one of the most classic attempts at this feat of building a foundation of mathematics and of understanding is through this series of publications called the Principia Mathematica. And this was Bertrand Russell and Alfred North Whitehead back in 1910 through 1913, attempting to establish a first-order logical system that could then derive all of mathematics and serve as sort of the basis or the fundamentals of mathematics. And they actually thought that they had done this successfully. And it was only later that this, what turned out to be a house of cards ended up becoming unraveled. And people were later able to poke holes in this system or in this foundation and find essentially incompleteness or inconsistencies. And so this has often been called the Hilbert program. We want to find a complete and consistent set of axioms that will derive all of truth, all of mathematics, and everything can be built upon these foundational axioms. Complete means that it will encompass all possible scenarios or inputs, and consistent meaning that none of the axioms are contradictory. One axiom says if x is positive, then y should be negative. The other one says if x is positive, y should be positive. And now we have this conflict in those axioms. One mathematician who's really heralded as sort of the person that really opened the floodgates of these problems is Kurt Gödel. And Kurt Gödel created what's called Gödel's incompleteness theorem. And this basically says that there cannot exist in principle, and he proved this to be the case. So it's not like, we haven't found one yet, but he proved that you cannot have a complete and consistent set of axioms to then derive all of the systems of first-order logic. And so what's kind of shocking here is you have first-order logic, but first-order logic cannot even define first-order logic from within first-order logic. So we're trying to create a system of rules and axioms within a system that can then describe the entire system, and that fundamentally leads to paradox. And paradox is very bizarre, but I absolutely love paradox, and I think you should all love paradox. And the most simple example of paradox is the liar's paradox. This sentence is false. And this really encapsulates this whole concept here. This sentence is false. If that sentence is true, then the sentence claimed it was false. So that doesn't make any sense. If the sentence is false, then, oh my God, the sentence told you it was false. So it's not lying to you, so it must be true. But you came in saying the sentence had to be false, and that's, now it's saying that it's true because it's false. So you're stuck in a paradox. And the problem here is you have a sentence referring to the truth value of its own sentence. So this sort of self-recursive pointer really disrupts the system. And part of trying to describe first-order logic from within first-order logic is you're creating these pointers going outside of the system and pointing back into the system. And this leads to paradox. Another example is Bertrand Russell's paradox. And so this is involving sets. And a set is sort of a boundary or a grouping of variables, and you can describe properties of these variables or of these objects. So the classic example is, let's take a set, let's call it S, So set S. S is the set of all sets that do not contain itself. So now let's think through this set of sets that cannot contain itself. And we must ask the question, is S in S? Is S within its own set? So if S does not contain itself, then S was the set of all sets that do not contain itself, so then it must be in S. So if the set S is not in S, then it has to be in S. If S does contain itself, then it shouldn't be in the set because it's defined as not containing itself, right? So once again, we have a set referring to the nature of sets, basically a set trying to self-describe sets, and it leads to paradoxes. And it sounds abstract, but it is fundamentally a limitation here. Next up, we have Alan Turing's halting problem. And this is very, very similar. But once again, the digital computer kind of makes this first order logic real. So one of the questions with digital computers is that I want to write some code, and I'm a newbie, so I'm writing some code, and it might be bad. And sometimes when I'm writing code, it gets stuck in an infinite loop, right? And I mentioned that these are first order logical systems. So we can clearly spell out, if this, then that, if this, then that. Will it start looping infinitely? Or is it computing the answer and it just hasn't reached the answer yet? And this is actually a really hard problem in digital computation because you don't really know if the answer was right around the corner. You pulled the plug on what you thought was an infinitely looping computer, but actually it was 4 steps away from outputting the answer, and you pulled the plug. And so you assumed that it was going to loop forever, but it was not. And so the question here is, can we figure out if a computer is going to loop forever? So I'll give you an easy example. Find an odd number that is the sum of 2 even numbers. All right, so we all know in our heads this is impossible. 2 even numbers sum up to be an even number. But if you're a digital computer and you want to check, well, maybe there's some numbers out there that are even, but they add up to an odd number. Let's just go check all possible numbers. And eventually, either we'll find a solution where, we found 2 even numbers that added up to an odd number. Obviously, we're not going to be able to find that, but the digital computer doesn't know that. Or we're just going to loop forever, and you're actually never going to output anything ever, right? So that's kind of a problem here. And so, could we write a computer program that would know whether or not a given computer program with a given input is going to halt, or if it's going to loop forever? And this is what Alan Turing called the oracle machine, right? You're looking into this crystal ball, and you're able to see the future of this program with this input, and you know whether or not it's going to loop forever, or if it's going to halt. And now, let's, for the sake of argument, assume that we could write a digital program that would be able to know whether or not it's going to halt with that input or if it's going to loop forever. So we have our oracle program. Now let's write another program that uses the oracle program, and it says, if my program is going to run forever, then stop. And if my program was going to stop, then let's loop forever. So you could theoretically and in principle write a computer program that would essentially, you give it some input and it's going to do the opposite essentially of what the output says. And now we take that computer program and we feed it into itself. And so now we're looking at what would happen if this computer program that we just wrote is inputted into itself. If it loops forever, then it says it's going to halt, and then it loops forever. And if it's going to halt, then it's going to loop forever, but it should have halted. And so essentially we can build a paradox here. And this one is a lot trickier to think through. And even now, as I'm telling it to you, it's difficult for me to like think through the logic of how this is a paradox. But this is essentially the same paradox that arises from Russell's paradox and from this liar's paradox. And so what Alan Turing draws as a conclusion is that the oracle machine cannot exist, because if it existed, there would be paradox. And paradox, as we all know, is impossible. And so we cannot have a computer that exists if it's going to just fundamentally produce paradoxes, because they cannot run or not run, because they just can't exist because it's a paradox. So this is super wacky, but it's really amazing. And it should blow your mind, because what this means is that digital computers cannot describe the domain of digital computation. So just as you can't write a first-order logical system like the Principia Mathematica attempted to do, to then describe first-order logical systems, you cannot write a digital computer that will then describe all the domain of digital computers, because that's essentially what you would have to do to create the oracle machine. And so we have, kind of unsurprisingly, the same limitation to first-order logic that we have in digital computation. And so we need something else. There has to be more to this universe or to this world than just digital computers, because if your biology was a digital computer, or if your mind was a digital computer, you could loop infinitely. You could get stuck. Who's writing the code? The code needs to be written. You need meta code to write the code that writes the code that writes the code, right? There is infinite chances of looping, infinite chances of paradox. So really, there is no way that that biology is based in digital computation, only because there's so much never-ending paradox and infinite loops. Imagine trying to evolve a novel organism using only the principles of digital computation. You would have so many instances of infinite looping, of having just an absolute failure to even self-describe the system. There has to be more, right? From a metaphysics standpoint, if first-order logic was the only thing that existed, it can't even self-describe itself. And so we need something else to come in and describe it. Now, of course, I don't have the absolute answer for you. I don't know what it's going to be that we discover or what else could be out there. But this leads Roger Penrose to draw the conclusion: humans are not using a knowably sound algorithm to ascertain mathematical truth. Essentially, there has to be an additional form of computation occurring for humans to be able to grasp mathematical truth so quickly and so readily. He calls this non-computation, essentially referring to it being not digital computation only. He doesn't quite assert a solution to the problem. He talks about Platonic forms or tapping into some bigger sort of meaning or some sort of conceptual domain, but there's not really a clear answer. Non-computation is just that. It's a negation of digital computation as a limitation, but it doesn't necessarily assert the solution. Now, I think we can look to quantum mechanics and to quantum computers and say what is going on there, which might have some novel solutions to this fundamental first-order logical problem. So the particle is a binarization of the superposition. We have a particle that gets measured. It's here or it's there. It's yes or it's no. Particles are very much like these Boolean variables. They're very much like this first order logic. However, the particle has a wave function operating behind the scenes, governing what that particle is going to do and what it's going to collapse into. And so the first order logical system has a higher order system in place. And so it's not it's not incumbent upon the particles themselves to then describe the superposition. So essentially, we're looking to particle-like phenomena, aka first-order logic and digital computation, to then describe the domain of superpositions or to describe the domain of everything or metaphysically describe everything. And yet we have this supervening probabilistic wave function overseeing or underlying this digitized particle state. And so is there some sort of novel solution given to us in the superposition? And so I don't know what the answer is. I don't know what the math is going to end up looking like. But rest assured that quantum mechanics gives us new forms of logic and gives us new mathematics that might serve as sort of a new dream for describing that foundation. We now have new tools to describe what that foundation might be, but it is interesting or difficult to conceive of a logical system that's not first order because we're moving beyond those like simple true false values that we're used to. So anyways, I'll leave you with the mystery of non-computation. Next week, we'll be talking about quantum computers a little bit more in the context of induction and how the Bayesian logical system is much more coherent with the view of quantum computers going through these iterative phases of wave function collapse, and how that is very much akin to the Bayesian model of inference. And so more on that in the next video. Hope you enjoyed this, and I'll talk to you again real soon.